Thank you for introduction. Yeah, I'm going to talk about, like Ludwig yesterday said, we're going here to discuss 20th century and 21st century maths. I will proudly join Paulo's team and we'll be talking about 20th century math. But in fact, the math that I'm going to cover was originated kind of like in even late 19th century. But the tools and the language for attacking these problems are actually from the very, very late of 20th century, not 21st. So therefore, this problem may look classical, but like real advantage was achieved only recently. I'm going to talk about linearization problems. Linearization problem. Let me shortly write Cremona 2, and I'll explain what it means. And it's with Antoine Pinardin, myself, and Igor Yasinski. Okay, so the main object of our interest and of interest of equivariant birational geometry in general is the so-called Cremona group, which is defined as the group of birational automorphisms of Pn. So, and all my talk will be over C. Yes, although the vast majority of the results can be extended over arbitrary field, and there are a lot of papers about it. But like today, I'm going to be focused only on C. So Cremona N is by definition the group of birational automorphisms of n-dimensional projective space. And I mean, since it's a very natural group, and it actually it contains a lot of interesting geometry in it, it's an object of a vast interest of mathematicians for nearly 200 years. And there are many results about the Cremona group, structural, such as whether it's simple or not, and the non-simplicity of Cremona was achieved quite recently, like roughly 15 years ago. It's not simple. People study subgroups of Cremona group, etc. And in my talk, I am going to be focused on the problem of classification of finite subgroups of Cremona group. So let me highlight this. There is a general goal: classify all subgroups. Let me say finite subgroups for simplicity. Of Cremona and unfortunately, it seems like this problem is very hard to achieve, but there are some partial results. And during my talk, I'll be focused for the case where n is equal to. So what do we know about Cremona 2 and what do we know about its subgroups? Well, for example, I believe that everything started with the following result of Noether and Castelnuovo, which is like roughly around 8071, is that Cremona group of plane is generated as a group by PGL3 and one special involution that I'll denote as I. Well, obviously PGL3 is a subgroup of Cremona because biregular automorphisms are also like birational. And let me define this involution I. So what I does, I'll write it down in coordinates. It takes homogeneous coordinates x1, x2, x0, x1, x2, and sends it into x1, x2, x0, x2, and x0, x1. Well, one can check straightforwardly that this element is indeed of order 2. It's so-called Cremona involution. And this element is enough to generate whole Cremona group. Well, in particular, this actually shows us that Cremona 2 is generated by involutions. And therefore, I believe the first natural step in studying Cremona 2 was, okay, can we classify orders of element 2 in Cremona 2 up to conjugation? Because we know that Cremona is generated by involutions. And in fact, we can. Let me construct a couple of examples, and then I'll tell you the classification result. Example. Let me do it quickly because we're kind of out of time. So let me construct the first involution. Let P1, P7 be points on P2 in general position. And let L be the linear system of cubic passing through this point. The linear system of cubics passing through these points. Well, then one can check straightforwardly that the dimension of this linear system is actually 2. Okay, now let me choose a point, a general point on P2. Let P be a point, a general point. And let LP be a subsystem of L of cubics passing through P. Well, then LP has the 9th base point. Then there is 9th base point of this linear system. Which I'm going to, And like after this construction, let me explicitly construct U1 involution. Let gamma work as following. It takes my point P and assign to it this gamma of P, which is by definition the 9th base point. Well, one can show that, I mean, first of all, we got a birational map from P2 to P2, but also one can show that this is actually involution, and it has a name. It's a Geyser involution. Where's the reason? Let me construct, but briefly because we started kind of late and we don't have much time. Let me construct. Let me construct another example, the so-called Bertini involution. So Bertini involution is very similar to Geyser one. However, we start with 8 points. We will do like a similar cubic trick, but starting with 8 points. let P1 and P8 in P2 be points in general position. And then let L be, again, the system of cubics passing through all these points. The system of cubics passing through these 8 points. Okay? But like by Bezout theorem, L has the ninth base point, which I'm going to denote it as P9. Yeah. And now this is already enough for me to construct a birational involution. I take, again, a general point. And what I do, I claim that there exists an unique cubic CP from this linear system L passing through P. And now I define a map that does the following. I denote it as beta. It takes P and sends it to beta of P, which is by definition is minus P, where this minus is minus on this elliptic curve with respect to P9, where P9 is fixed as 0. This is also involution. And the third one, let me probably squeeze it here, and let me break the order, is the so-called the Jonquière involution. And again, due to the lack of time, I will just write down the equations of this involution.
I'm sorry,
yeah.
I missed the definition of minus P. So what is minus P?
Yeah.
It's minus P from cubic.
Yeah, from the cubic with respect. So in order to define a group law on a cubic, I need to fix 0, and this 0 will be P9. Yeah. So, and the Jonquière involution. The Jonquière involution is involution that locally in affine coordinates looks like this. fxy equals to x p of x over y, where p of x is a polynomial of odd degree. And we can assume that it has no multiple roots. Well, this may not be obvious that this guy is indeed an involution, but it is an involution. Again, I'm just trying to wrap this up. Believe me. So what's the theorem? The theorem is proved, relatively recently, given the scales of the problem, right? 8071. So the theorem says that, which I probably will write down here, is that's it. There are no more involutions in Cremona group. And it's theorem due to Bayle and Arnaud Bouville. Bouville in 2000. So look how long did it take to mathematicians to prove this theorem, although there were attempts back in days, but the proofs were lacking of rigorous proof. So what did they prove? That every involution in Cremona group, we're talking about only Cremona 2, is conjugate to a linear one. I mean, obviously, because there are linear subgroups. And these three guys only, Geyser, Bertini, de Jonquière, and nothing else. Well, I believe this is the first theorem, the conceptual theorem on some sort of rigorous classification of subgroups up to conjugation. And this is something that we are essentially looking for in this whole equivariant stuff and in the global problem of classifying subgroups of Cremona 2.
I think they assume characteristic 0.
Hey,
I think they assume.
I
can check.
I'm highly convinced that they're working overseas.
They do work overseas, but
Yeah.
I think does the proof work?
Yeah.
Maybe not. The way characteristic 2 maybe.
Sure. How about 3?
Yeah, but also it does not work over non-closed field.
Because this is definitely wrong.
Yeah, because we have classics of algebraic birational geometry, we know the theorem. So yeah, the list is way longer. There are like 13 unique involutions over R. Am I right?
Algebraic closed field of characteristic.
Okay. Well, again, let me skip some parts of it. Okay. What else can we say about finite subgroups of Cremona 2? Well, there were a lot of work after this paper in 2000s, but probably the main highlight is the result of Jeremy Blanc, who classified all finite subgroups, all finite abelian subgroups of Cremona 2 up to conjugation. He did a very good job, but I would like you to give the list of the subgroups, just the isomorphism classes, to see how few they are in some sense.
So may I ask you, what is basically roughly the idea of this proof?
Pardon?
What is roughly the idea of proof of this?
Oh, we will discuss it because the same idea will be used in my main result. Here again, I'll be there because so far I'm just giving some algebraic subgroups and there is no algebraic geometry, right? Besides of the motivation of my talk, but geometry will start very soon. Okay, so theorem of Blanc, 06. Again, he proved way more, but let me simplify his result. The isomorphism classes of finite abelian subgroups of Cremona 2 are ZMZ times ZNZ for any m n bigger or equal 1. Well, that one is easy. Then something odd, so something even times Z2 Z square for n bigger or equal 1. This third one is z4z square plus z2z z3 cube, and the last one z2z power of 4. And that's it. And he described it, as I said, up to conjugation. So you can see that there are not that many finite abelian subgroups in Cremona 2. And after this paper, in like 3 years later, Iskovskih and Dolgachov classified all finite subgroups of Cremona 2. However, their paper is quite big and it's quite difficult to go through it. And some part of the class on their classification is not even up to conjugation, but up to isomorphism. So therefore, we technically know the list of finite subgroups, but if you give me a subgroup and ask me whether it can be if you give me a group and ask me whether it can be a subgroup of Cremona 2 or not, I can't just go through their list and say, oh, yes or no. So therefore, we know pretty much a lot about isomorphism classes, but not everything. And as you can see, the problem is getting harder and harder. And maybe the goal that I initially wrote here is not that easily achievable. Maybe we should study some more natural subclass of subgroups of Cremona 2 and hope that there is a feasible classification for them. And I have such a subfamily. It's also quite natural. Let me give the following definition. The idea is that in order to classify finite subgroups of Cremona 2, we want to, first of all, know which one comes from PGL3, right? Therefore, we have this definition. A subgroup finite subgroup of Cremona 2, of any Cremona, is called linearisable if it is conjugate to a subgroup of PGL3 living in Cremona 2. So what this definition means, as I said, we want to study those groups, those subgroups that come from PGL3, keeping in mind that we understand the subgroups of PGL3 well enough. It's a classic 200 years old, roughly, result. Okay, so maybe we can classify them. And the answer is yes, we can, and we can do it up to conjugation. So we can describe all conjugancy classes of such linearizable subgroups. However, in order to do it, I need to provide you with some geometric reduction, as was requested earlier, because this geometric reduction will allow us to understand better, should provide us with a language of working with conjugacy classes and how to describe them.
Excuse me.
Yeah.
So this is Cremona n.
Oh yeah. I should. Yeah, I started with indeed. It's n plus 1, Cremona n. Yeah.
Thank you.
Yeah, I was keeping in mind my answer. Okay. So let me describe you this geometric reduction. So say I have P2 that is which is acted birationally by a finite subgroup G, right? Well, first of all, let me resolve the indeterminacies of this action. According to classical result of the best of my knowledge is determinate, we can always resolve indeterminacy and find a smooth projective. Isn't it determinate? Sorry?
It's Italian, but it sounds French. Yes. Fancy. He was asking how it's pronounced.
Determinate, no?
Yeah.
Yeah.
Thomas, so yeah. So according to his wonderful result, we can always resolve indeterminacies of such a birational action and find a smooth projective surface which is acted by G, but biregularly already. This is a biregular action, and this guy is smooth, projective, and G is a subgroup of automorphismal bits. Well, that's already good because we would rather work with biregular action than birational. However, we have a problem. There is a price to pay, and this price is that I obtained X by some rather unpleasant sequence of some embedded blowups. So X has quite a bad structure. We want to simplify X as much as we can. But can we? The answer is yes, we can. We can run the so-called G equivariant minimal model program, GMMP, and we will end up with a surface S, which is also acted biregularly by the group G. And by the way, all these dotted arrows are equivariant. So I keep track of the action of my group. And the output is the so-called G-Mori fiber space, which is a surface of two types. Which is either S is a Delpezza surface with invariant Picard group of rank 1, or S is a conic bundle and equivariant Picard group of S. Okay, I should put rank is equal to. So it's like a regular minimal model program, but with a twist, right? If we let G equals 1, we will get our regular minimal model program. Therefore, sometimes as an output of this minimal model program, you can get a G-Mori fiber space, which is not Mori fiber space in the classical sense. My favorite example, for instance, take the Delpezza surface of degree 5 and let G be S5, the full group of automorphisms of this Delpezza surface of degree 5. Then, of course, Delpezza surface of degree 5 itself is not a Mori fiber space, right? Because we can contract further to P2, for example. But it is S5 Mori fiber space because the full group of the full automorphism group permits all -1 curves together. So there is no like equivariant contraction of something smaller. Okay, now what I've done is by a subgroup in Cremona 2, I've constructed a couple of a surface and group G such that S is a G-Mori fiber space, right? But in fact, we can go in the opposite direction. But the problem is we may not arrive back to the group G, but we will hit a subgroup that is conjugated to it. So therefore, in order to make it sort of like 1 and 1, like here, I should twist it and say conjugacy class of G in Cremona 2. And that's it. That's all I need. Instead of thinking about some abstract conjugacy class, I should think about G-nil surface, finite subgroup, and of course, probably up to some G-equivariant birational automorphism. Well, now this language will allow me to work efficiently with these conjugacy classes. And now we are ready to formulate our main result on the language of this side of like geometry.
This is really Tomaso's. I thought this is classical.
Oh, no, like Tommaso was this part.
Really?
Well, sorry. I mean, that's the only reference I know. I'm too young to know all.
Tommaso gave the proof. It was, of course, known by everyone, but there was no, how to say, written proof in the class.
I thought it was Whale.
Yeah, maybe it goes back to Whale.
Yeah.
So quick before Tomaso. No offense for Tomaso.
I'm too young to know this. Sorry.
Well, I'm also too young to Whale, to be honest.
Yeah. So okay, probably in the remaining part, I will. Okay, let me finally formulate the proof, and then I'll sketch the sorry, let me formulate the theorem, and then I'll sketch the proof.
By the way, conjugation this classification up to identity.
No, but
Up to conjugation, it's actually absolutely wrong.
conjugation in of abelian subgroups?
No, I mean this is.
But that's what is written, right?
Yeah, but what I want to stress that conjugation is absolutely open, so it's a big problem. Even like for Z2 times Z2.
I thought he sorted
No.
conjugation. Okay.
But in particular case, when you have first case m equal 2, n equal 1, some infinitely linear evolutions.
Yeah.
Up to conjugation is one of the following, but they don't know.
Yeah.
Conjugacy classes not discussed.
Okay.
But people work.
Okay, so let me state the main theorem, but we got. So it's going to be kind of like a long list, but an explicit one. Okay, theorem by Narda, myself, and Yasinski. So let G be a subgroup of finite subgroup of Cremona 2, and let S be a G-Mori fiber space, which is obtained like through this way over the base B. By base, I mean like its point in this case and its P1 in this case, right? Then G is linearizable if and only if the pair SG is one of the following. Okay, now there'll be a nice big table. So I'll put the degree, the surface S, and the group G. Oh, I don't need that much. Okay, so let me start describing from the conic bundle case. So G conic bundles. Okay, what are they? So here we'll always have 8. So it'll be Fn, n is odd, and any group is just regularizable. 8, now Fn is even, n is even. And here we have the condition that if G acts on P1 as a cyclic group or as odd dihedral group. It's odd number. And the last case here will be P1 cross P1, which is F0. But it is special because in this case, we say even more precisely, we say that G is one of the following. It's either a fiber product of two cyclic groups, or it's a fiber product of a cyclic group with a dihedral group of odd order, and two odd dihedral over Q. And if this is isomorphic to a dihedral group, some D n. And that's everything that can be linearized on conic bundles. And what about?
So for her specific, P1 is the base.
Yeah. It's just conic bundle. Yeah. B isomorphic to P1. Okay, and for G Delpezza surfaces, oh yeah, these surfaces are often referred as G Delpezza surfaces. And for G Delpezzas, we have the following. So G Delpezza, we have degree 5, it's unique. And here we have C5 or D5, which are also unique up to conjugation in this automorphism group. Delpezza of degree 6, also unique. Here it's cyclic group of order 6 and S3. But here there are infinitely many of them, right? Because the automorphism group is infinite. 8, it's P1 cross P1. But when the equivariant Picard group is 1, so I should probably say that rank of equivariant Picard group here is 1, unlike here. Therefore, the groups are different. And we view these P1 slightly differently from this P1. And here we have this very odd extension. We have fiber product of two cyclic groups extended with an involution that swaps these two fibers. And I mean, like, technically speaking, and if it's P2, then it's any group, right? So this is the list, and this is the and this is it. There are no more conjugancy classes. There is a small problem is that these conjugancy classes are not mutually exclusive. They do intersect. Because, I mean, sometimes you can you can be on G-Delta surface and you can construct an equivariant birational map to a conic bundle, and you'll end up somewhere here. But it's perfectly fine. And for applications, this is I believe, it's a very useful list. So in the remaining, I'll say 5 minutes, I'm going to explain like the sketch, the proof of these results, and how in general the results about finite subgroups of Cremona, not only 2 but higher, can be achieved. Yeah, let me be a bit short here. So
Excuse me, but what is Q on the?
yeah, Q is a group. It's a fiber product of these 2 groups over Q. I mean, Q is a group that admits a surjective homomorphism from these 2 groups. And we do not have a control over Q, and it's actually good. Like it's easier to control these factors due to the proof than this Q. And very often in applications, you do not care about this Q. You care about what acts on P1 and P1. Basically, these groups here, like CN, CM, and etc., are the groups that act on this P1 and this P1 correspondingly. And then they can somehow glue together, and that gluing method is this fiber structure. Okay, so now how to prove this result? How do people prove results like this? Well, very easily. So you see, according to this reduction that I said, you start with a G-Mori fiber space. Technically speaking, it can be over some base, which is point or P1. And you ask yourself whether there exists a G-equivariant birational map, G-map, birational map, to P2, right? Or not? Well, if I give you any 2 varieties and ask this question, whether there is a equivariant birational map between them or not, you will struggle to, one will struggle to answer to this question. However, in this particular situation, there is a technique allowing us to study existence and non-existence of this map, because we're studying birational maps between G-Mori fiber spaces. And if you're in such a situation, then there is a beautiful result, originally by Sarkis and then proved by many other mathematicians, sorted like quite recently all dimensions. I believe it's McKernan and Haken in 2009, they proved this program, all generalities, that basically says the following. If such equivariant map exists, then it can be decomposed, non-uniquely, but decomposed in a sequence of elementary transformations. And these elementary transformations are referred as Sarkisian links, and in dimension 2, they're classified. Roughly speaking, it's some sort of transformation that blows up an orbit, constructs something else, and then blows up, and then you do this sort of like diagrams, and then eventually you hit P2, or you do not hit P2, and it really depends on the geometry of your surface and also on the geometry of your group action. How to prove this result? Well, you take a G-Delta surface. Okay, you take an E-Delta surface. First of all, you classify all subgroups with respect to which it becomes a G-Delta one. So with respect to which its equivariant Picard group is 1. The rank of equivariant Picard group is 1. And then you ask yourself, okay, what are the possible Sarkisian links from this group, from this surface with respect to this group? And then you just explore case by case, and you show whether you can hit P2 or you cannot. It sounds easy, however, things become drastically difficult after degree 6 as the group, the automorphism group becomes infinite and it's very hard to study. So therefore, there's a lot of group theoretical work has been done on this side of the project. And then you also need to classify all orbits and things become basic. But like once you sort out this stuff, the rest of this proof is sort of this diagram chase, but 19th century, 20th century diagram chase. And yeah, I think I was asked to be only 50 minutes. I'm going to stop here.
Okay. Question.